Welcome to this problem walkthrough. Today, we'll be exploring an interesting dynamic programming problem titled Uncrossed Lines. This problem challenges us to find the maximum number of matching pairs between two sequences while ensuring the lines formed by these matches don't cross. Let's dive in and uncover the optimal solution together. In this problem, we are given two integer arrays, nums1 and nums2, and we need to draw connecting lines between their elements under specific conditions. A connecting line can only be drawn between two numbers if their values are equal, that is, nums1, I, equals nums2, j. Additionally, these lines must not intersect with each other. This means that the lines cannot cross over or share a common endpoint. Your task is to determine the maximum number of such uncrossed lines that can be drawn between the two arrays. The output will be an integer representing this maximum number of lines. To better understand the problem, let's look at an example. Suppose nums1 is 1, 4, 2, and nums2 is 1, 2, 4. In this case, the maximum number of uncrossed lines is 2. Specifically, you can connect nums1, 0, which is 1, to nums2, 0, also 1, and nums1, 2, which is 2, to nums2, 1, also 2. Notice that these connections do not intersect, and the number 4 in both arrays is left unconnected. This demonstrates how we aim to maximize the number of lines while ensuring they remain uncrossed. Now consider another example where nums1 is 2, 5, 1, 2, 5, and nums2 is 10, 5, 2, 1, 5, 2. Here, the maximum number of uncrossed lines is 3. The connections that achieve this are nums1, 1, 5, to nums2, 1, 5, nums1, 2, 1, to nums2, 3, 1, and nums1, 3, 2, to nums2, 5, 2. Each of these lines satisfies the conditions for being drawn, and no two lines intersect. This example highlights how elements can be matched even if the arrays have different lengths or contain repeated values. Let's look at a third example. Here, nums1 is 1, 3, 7, 1, 7, 5, and nums2 is 1, 9, 2, 5, 1. In this case, the maximum number of uncrossed lines is 2. We can connect nums1, 0, 1, to nums2, 0, 1, and nums1, 5, 5, to nums2, 3, 5. Importantly, even though there are other matching elements, such as the 7s, connecting them would result in lines crossing. The constraints ensure that we must avoid such intersections. This example also demonstrates how the solution is not always immediately obvious and requires careful planning to maximize the number of valid connections. Finally, let's consider some edge cases. First, since the arrays are guaranteed to be non-empty, we don't need to worry about handling empty inputs. If nums1 and nums2 have no common elements at all, the output will simply be 0, as no lines can be drawn. If the arrays are identical, then every element can be matched one-to-one, and the output will equal the length of the arrays. Lastly, for large arrays with duplicate values, the algorithm must handle repeated elements efficiently while ensuring that no lines intersect. These edge cases underline the importance of designing a solution that is both robust and optimized for performance. To tackle the problem of uncrossed lines, we first considered a brute force approach. The idea here is to interpret the task as finding the maximum number of matching pairs between the two arrays, nums1 and nums2, with the condition that no lines connecting these pairs intersect. Using recursion and backtracking, we could try all possible ways to match elements from the two arrays and ensure the non-crossing condition is satisfied. However, there are key observations that make this challenging. The problem is analogous to finding the longest common subsequence, or LCS, of the two arrays, where a valid match occurs only if the elements are equal and the indices maintain the non-crossing condition. While this approach is simple to understand, its time complexity is exponential due to the combinatorial nature of backtracking, making it impractical for larger inputs. The space usage is also proportional to the recursion depth, making it less scalable. Thus, while straightforward, this method is computationally infeasible beyond small cases. A more efficient solution involves using dynamic programming, based on the insight that this problem is structurally similar to the LCS problem. We define a DP table where DP, I, j, represents the maximum number of uncrossed lines that can be formed between the first I elements of nums1 and the first j elements of nums2. The recurrence relation here is key. If the elements nums1, I1, and nums2, j1, match, then we can add this match to the solution for the subproblem that excludes these elements, i.e., dp I, j equals dp I1, j1, plus 1. Otherwise, we take the maximum result from either excluding the current element of nums1 or nums2, expressed as dp I, j equals max, dp I1, j, dp I, j1. This iterative process is what fills the dp table. The algorithm begins by initializing a 2D table of dimensions, len, nums1, plus 1, x, len, nums2, plus 1, and then iteratively applies the recurrence relation. The value at dp, len, nums1, len, nums2, gives the final result. This approach efficiently captures the non-crossing constraint and enables us to handle larger inputs with ease. The dynamic programming solution has a time complexity of O, m*n, where m and n are the lengths of nums1 and nums2. This is because we compute the value of each cell in the dp table exactly once. The space complexity, however, is also O, m*n, due to the 2D table used to store intermediate results. For scenarios where memory usage is a concern, this can be optimized to O, min, m, n, by using a rolling array. Instead of maintaining the entire dp table, we use two 1D arrays to represent the current and previous rows of the table. This significantly reduces memory usage while preserving the correctness of the solution. The algorithm iteratively updates these arrays, ensuring that state transitions follow the same recurrence relation. This space-optimized version is a bit more complex to implement but is highly effective for memory-constrained environments, making it a practical alternative to the standard dp table. Considering the trade-offs, the dynamic programming approach stands out as the most balanced solution for this problem. While the brute force method is computationally impractical for larger inputs, the dp solution is both scalable and efficient. The standard dp implementation, with its simple structure and straightforward debugging process, is particularly well suited for understanding the problem and verifying correctness. On the other hand, the space-optimized dp is ideal for scenarios where memory constraints are critical, though it requires a bit more complexity in implementation. By framing the problem as a variant of the longest common subsequence, we leverage well-established techniques that ensure both efficiency and accuracy. This makes the dp approach the clear choice for solving the uncrossed lines problem effectively. To solve the problem, the goal is to find the maximum number of matching pairs between two arrays, nums1 and nums2, without forming crossing lines. This is essentially a variation of the longest common subsequence problem, but here we have the extra condition of preventing crossings. To ensure lines don't cross, we need to preserve the order of indices. For two matches, I1, J1, and I2, J2, where I1, I2, it must also be true that J1, J2. This ensures that the matches form an increasing subsequence in both arrays. With this condition in mind, the first step is to map elements of nums1 to the indices where they occur in nums2. For example, if nums2 is 3, 1, 2, 3, the mapping would store the indices of each value, such as 3, 0, 3, 1, 1, 2, 2. Then, for each element in nums1, we replace it with the corresponding indices from nums2. For instance, if nums1 is 1, 3, 3, 2, this mapping produces 1, 0, 3, 2. At this point, solving the problem reduces to finding the longest increasing subsequence of these indices, which ensures the matches do not cross. The next step is to find the longest increasing subsequence, or LIS, from the transformed list of indices. To do this efficiently, we can use a greedy algorithm combined with binary search, achieving a time complexity of O, n log n. The process begins by initializing an empty list, LIS, to store the smallest ending elements of increasing subsequences. As we iterate through the indices in the transformed list, we use binary search to determine where the current index fits within LIS. If the index is greater than all elements in LIS, we append it to the list. Otherwise, we replace the first element in LIS that is larger than or equal to the current index. This ensures that LIS always stores the smallest possible ending elements, allowing us to build the longest increasing subsequence efficiently. Once all indices are processed, the length of LIS gives the size of the LIS, which corresponds to the maximum number of matching pairs without crossing lines. This reduction to the LIS problem is key, as maintaining the order of indices in nums2 ensures that no crossing occurs. The binary search approach is crucial here, as it allows us to compute the LIS in optimal time. To implement this approach, we use two main data structures. The first is a dictionary, which maps each value in nums2 to its indices, enabling quick lookups of possible matches for elements in nums1. The second is a list to store the smallest ending elements of increasing subsequences, which is used to compute the LIS. The algorithm handles several edge cases effectively. For instance, if either array is empty, the result is 0 since no matches are possible. Similarly, if there are no common elements between nums1 and nums2, the result is also 0. On the other hand, if all elements match in order, the result is simply the length of nums1 or nums2. The algorithm also accounts for duplicates in nums2 by considering all occurrences of a value during the mapping step. In terms of complexity, the mapping step takes O, n plus m, where n and m are the lengths of nums1 and nums2, respectively. The LIS calculation is O, k log k, where k is the size of the transformed list. Combining these, the overall time complexity is O, n plus m plus k log k, making the solution efficient even for larger inputs. This implementation solves the uncrossed lines problem using dynamic programming. The problem is essentially a variant of the longest common subsequence, LCS, where we aim to maximize the number of matching pairs between two arrays without crossing lines. First, we initialize the lengths of the two input arrays nums1 and nums2 as m and n. A dynamic programming, DP, table DP of dimensions m plus 1 and x n plus 1 is created, where DP, I, j, represents the maximum number of uncrossed lines that can be formed using the first I elements of nums1 and the first j elements of nums2. The table is initialized with zeros. The nested loops iterate through each pair of indices, I, j, in nums1 and nums2. If the elements nums1, I1, and nums2, j1, match, remembering that DP is 1-based while arrays are 0-based, we add 1 to the maximum value obtained by excluding these elements, DP, I1, j1. Otherwise, the value at DP, I, j, is taken as the maximum of the values DP, I1, j, and DP, I, j1, representing the best result by excluding either the current element of nums1 or nums2. Finally, the result is stored in DP, m, n, which represents the maximum number of uncrossed lines for the entire arrays. The algorithm runs in O, m asterisk n, time with O, m asterisk n, space, where m and n are the lengths of nums1 and nums2, respectively, making it efficient for this problem's constraints. This is the Java implementation of the uncrossed lines problem, mirroring the dynamic programming approach used in the Python solution. The solution uses a 2D array DP to store intermediate results, where DP, I, j, represents the maximum number of uncrossed lines that can be drawn between the first I elements of nums1 and the first j elements of nums2. The code uses nested loops to fill the table, comparing elements of the two arrays and updating the table based on whether the elements match or not. Key differences from Python include explicit type declarations, use of math.max for comparisons, and Java-style array initialization and indexing. To solve the uncrossed lines problem, we use dynamic programming to determine the maximum number of matching elements between two sequences without crossing lines. Starting with our first example, we have nums1 as 1, 4, 2, and nums2 as 1, 2, 4. The lengths of these arrays are both 3, so we initialize m and n to 3. Next, we create a DP table of size, m plus 1, by n plus 1, which in this case is 4 by 4, and initialize all the cells to 0. This table helps us store intermediate results. Now, we begin filling the table. For the first pair of indices, I equals 1 and j equals 1, we compare nums1, 0, which is 1, with nums2, 0, which is also 1. Since they match, we increment the diagonal value dp, 0, 0, by 1 to get dp, 1, 1, equal to 1. At this point, the dp table has been updated to reflect the match. The value at dp, 1, 1, is now 1. For the next comparisons, when I is still 1 but j progresses to 2 and 3, we find that nums1, 0, does not match nums2, 1, or nums2, 2. In these cases, we use the maximum value from either the top or the left cell. This means dp, 1, 2, becomes the maximum of dp, 0, 2, and dp, 1, 1, resulting in 1, and similarly, dp, 1, 3, also becomes 1. As we continue filling the table for I equals 2 and I equals 3, we account for matches and mismatches in a similar fashion. By the end, the final dp table looks like this, the first row remains unchanged, the second row has values 1, 1, and 1, the third row updates to 1, 1, and 2, and the fourth row ends up with 1, 2, and 2. After completing the DP table for this example, we can extract the result from the bottom right corner. The value at DP 3, 3 is 2, which means the maximum number of uncrossed lines between nums1 and nums2 is 2. Now, let's look at another scenario where all the elements in the two arrays match. For nums1 is 2, 5, 1, and nums2 is 2, 5, 1, we initialize m and n to 3 and create a new DP table of size 4x4, filled with zeros. During the filling process, since every element in nums1 corresponds directly with nums2, the diagonal values are increment 1 by 1. Specifically, dp 1, 1 becomes 1, dp 2, 2 becomes 2, and dp 3, 3 becomes 3, reflecting that all elements contribute to the uncrossed lines count. At the end of this second example, the DP table reflects the perfect match between the two arrays. The table's final state shows the progression of the uncrossed lines count. The bottom right corner, dp 3, 3, holds the value 3, indicating that all elements are part of the solution, and the maximum number of uncrossed lines is 3. Lastly, let's consider a case where there are no matching elements between the two arrays. For nums1 is 1, 3, 7, and nums2 is 2, 6, 4, we once again initialize m and n to 3 and create a new DP table of size 4x4, filled with zeros. In this final example, as we fill the DP table, we compare each element of nums1 with each element of nums2. Since no elements match, the value in every cell of the table remains 0. The final DP table is completely filled with zeros, indicating that there are no uncrossed lines possible between these two arrays. The result, as represented by dp 3, 3, is 0. This concludes the step-by-step execution for all three cases, showing how the dynamic programming approach adapts based on the input arrays to compute the maximum number of uncrossed lines. The time complexity of our dynamic programming solution is O, m*n, where m is the length of nums1 and n is the length of nums2. Let's break this down step by step. First, we initialize a 2D DP table of size m plus 1 by n plus 1. This involves setting each cell to 0, which requires O, m*n, time since we are iterating through the entire table. Next, we fill the DP table by iterating through all combinations of indices I from 1 to m and j from 1 to n. For each pair, we perform a constant time comparison, nums1, I1, equals nums2, j1, and based on the result, access neighboring cells like dp, I1, j1, dp, I1, j, or dp, I, j1, followed by simple arithmetic or a max operation. Since processing each cell takes O1 time and there are m*n cells, filling the table also requires O, m*n time. Finally, returning the result stored in dp, m, n is an O1 operation. When we combine these steps, the overall time complexity is dominated by the initialization and filling of the DP table, resulting in O, m*n. The space complexity of this approach is also O, m*n, and here's why. The primary contributor to space usage is the DP table, which has dimensions m plus 1 by n plus 1. Each cell in this table stores an integer, and assuming each integer takes O1 space, the memory required for the table is proportional to the number of cells, resulting in O, m*n space. Additionally, the algorithm uses a few auxiliary variables such as m, n, I, and j. Since these variables require constant space, their contribution is negligible compared to the DP table. Therefore, the total space complexity is determined by the DP table, making it O, m*n. To understand the efficiency of the dynamic programming solution, let's compare it to a naive or brute force approach. A brute force solution would involve examining all possible subsequences of nums1 and nums2 to determine the maximum number of matching pairs without crossings. Since there are 2 to the power of m subsequences for nums1 and 2 to the power of n for nums2, the total time complexity for this approach would be O, 2 to the power of m*2 to the power of n, which is exponential and highly inefficient. On the other hand, the dynamic programming approach avoids this exponential growth by reusing intermediate results stored in the DP table. By solving overlapping subproblems only once, the complexity is reduced to O, m*n. Now consider the best, worst, and average cases for the DP solution. Even in the best case, where all elements of nums1 and nums2 match perfectly, or the worst case, where there are no common elements, the entire DP table still needs to be filled. This means that the time complexity remains O, m*n in all scenarios, including the average case. Finally, let's solidify our understanding with a mathematical proof for the big O complexity. The time complexity arises from the nested loops that iterate exactly m*n times. Since each iteration involves constant time operations like comparisons and arithmetic, the total time complexity is O, m*n. For the space complexity, the DP table consists of m+1*, n+1 cells, each requiring O1 space. This results in a total space complexity of O, m*n. Both the time and space complexities are therefore O, m*n, making this dynamic programming approach significantly more efficient than the brute force method, which suffers from exponential growth. The DP approach demonstrates how breaking a problem into manageable subproblems and reusing results leads to an elegant and efficient solution. When solving the uncrossed lines problem, there are several common mistakes to watch out for. First, misunderstanding the non-crossing condition can lead to invalid solutions. Remember, any matched lines between nums1 and nums2 must not cross, which is why this problem is fundamentally about finding the longest common subsequence, or LCS, under specific constraints. Ignoring this condition might lead to greedy or brute force approaches that fail to validate the correctness of the matches. Another frequent pitfall is relying on naive brute force methods. While it might seem intuitive to try all possible pairs between the two arrays, this quickly becomes computationally expensive, especially for larger input sizes. A brute force approach with a time complexity of O(n²) or more is rarely practical. Lastly, failing to handle duplicates correctly can lead to subtle errors. For example, if both arrays contain repeated values, it's crucial to distinguish between identical elements at different indices to ensure the solution respects the order of elements in each array. Neglecting this can result in mismatches that violate the problem's constraints. In addition to those mistakes, overlooking edge cases can often derail a solution. For example, if either nums1 or nums2 is empty, or if the arrays have no common elements, the program should handle these scenarios gracefully and return a result of 0 matching pairs. A robust solution must account for all possible inputs, no matter how trivial they seem. Another issue is overcomplicating the solution. Sometimes, candidates introduce unnecessary steps or extra data structures, which can inflate the space complexity and make the algorithm more difficult to debug or explain. It's important to focus on simplicity and efficiency. Over-engineering the solution might not impress an interviewer and could lead to mistakes during implementation. Strive for clarity and optimal resource usage to ensure both correctness and performance. To perform well in an interview, it's crucial to recognize that this problem is a variation of the longest common subsequence, or LCS. The dynamic programming approach to LCS naturally satisfies the non-crossing condition, which makes it an ideal solution. This insight can save you time and help you focus on implementing an efficient algorithm. Additionally, this problem fits into the broader category of matching problems where maintaining relative order between elements is key. Identifying this pattern early allows you to connect it to other problems like LCS or interval scheduling, which share similar principles. When discussing your approach, emphasize the trade-offs between brute force and dynamic programming. For instance, DP achieves a time complexity of O(n²), with space optimizations that can reduce memory usage to O(n) or O(min)(n)m using rolling arrays. Always consider edge cases during your explanation, such as empty arrays or arrays with no overlap, and be ready to justify why your solution is robust. Lastly, clearly articulate why dynamic programming provides the optimal balance of efficiency and correctness compared to alternative methods like greedy algorithms. When preparing for this problem, it's helpful to explore related problems that reinforce the same concepts. For example, LeetCode 1143, longest common subsequence, is directly related since it shares the same core dynamic programming approach. Similarly, LeetCode 72, edit distance, and LeetCode 392, is subsequence, highlight the importance of maintaining relative order between elements. These problems build a strong foundation for solving variations of the uncrossed lines problem. Now, let's discuss alternative approaches. The dynamic programming method is the most reliable. By constructing a 2D DP table where each cell represents the maximum number of matches for specific prefixes of nums1 and nums2, you can systematically compute the result. Although the time complexity is O and *m, space optimization techniques, such as rolling arrays, can reduce the space complexity to O, min, n, and m. This approach is efficient and robust, making it the preferred choice in most scenarios. Alternatively, a recursive approach with memoization can also solve the problem, but it introduces additional risks. While recursion simplifies implementation conceptually, it can lead to stack overflow for large inputs, which makes it less practical in certain situations. Another possible approach is greedy matching, where you iterate through nums1 and find the first matching element in nums2 that satisfies the non-crossing condition. While this method is simple and has a time complexity of O and *m, with minimal space usage, it is prone to failure for critical edge cases. For example, it struggles with inputs that require multiple non-adjacent matches or where the order of elements plays a significant role. This unreliability makes greedy algorithms unsuitable for solving the uncrossed lines problem in most cases. Instead, dynamic programming remains the most robust and scalable solution, as it carefully considers all constraints while maintaining computational efficiency. Exploring these alternative methods helps you understand their trade-offs, but for optimal results, sticking to the DP approach ensures both correctness and performance, especially when handling larger datasets or edge case scenarios. Great job! We've successfully solved the uncrossed lines problem using dynamic programming. This solution demonstrates how to identify and work with overlapping subproblems effectively. Remember, this approach is widely applicable to problems like longest common subsequence. Thanks for tuning in. Make sure to like and subscribe for more problem-solving content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!